Hello, everybody. Hey, this is a video on help with problem set number 1 from week 2. Here are all the answers from the back of the book. Now, usually I might not do that, but just for the sake of having all those answers in front of us, there they are. And the tricky problem in this problem set was definitely number 33. Even though some of the other questions, like even the tortoise and the hare problem number 9, the math was a lot simpler, but it was still, you had to stop and think about it and figure it out. Now, whenever you're doing any of these problems in physics, it is a good idea to know your equations. So we have our 4 basic kinematic equations there. Now, for you guys, particularly in the beginning, it's good to have them just right there in front of you. And I like the fact that I have these parts where when you're learning to figure out which equation you're going to use, it's good to know what variable is not in those, and you can see those listed, and you've seen me do a few examples there. It is also a really good idea to know what you are looking for. So probably the first step that you want to do is to read the problem and reread the problem and figure out what the question is really asking. And sometimes you might start the problem because particularly one like 33, where it's really kind of confusing and you got to do a lot of thinking, you might be doing some work and then really not answering the question. So you want to reread it till you know exactly what you want. Also, drawing a picture, or in this case, drawing graphs of what the motions are doing, can be really helpful for you understanding the question. So I'm going to kind of read it real quick. You've got a car and a bike, and the car can reach a maximum velocity of 50 miles per hour and have an acceleration that is equal to 9 miles per hour per second. And a bicycle is going to have a maximum velocity of 20 miles per hour, but a higher acceleration of 13 miles per hour per second. Now, I don't like all these mixed miles, hours, seconds. So what I did is I converted them all to meters per second or meters per second squared, which you will see in a moment. Okay, but the 2 questions that are asking in there is, for what time interval is the bicycle ahead of the car? And for what maximum time interval is the bicycle, or what maximum distance does the bicycle lead the car? Okay, so I'm going to move this over a little bit, and you can use dimensional analysis and convert miles per hour into meters per second, or miles per hour per second into miles or meters per second squared. But I've got a little shortcut in my head, and that is if you divide by 2.24, it's going to change miles per hour into meters per second. So we got 22.3 for the car, and 9 divided by 2.4 is 4 meters per second squared. For the bike, 20 miles per hour divided by 2.24, the maximum velocity is 8.93. Acceleration is going to be 5.8. So really what's happening, we want to look at what's happening in the graph. So the first one is going to be position versus time. So as you know by now, we're going to have a curved line for a constant acceleration. We're going to have a curved line, it's parabolic, and it's going to go up for a certain amount until it reaches its maximum speed, at which point, when it's going at a constant maximum or a constant speed, it's going to have a diagonal line like so. Now for the car, okay, now the car is also going to go up, and it's going to either have this situation, okay, where it's still accelerating when it passes the car, okay, at which point at another time it's going to reach its maximum velocity, or you could have something like this, and then it's going to speed up, and wherever these two points intersect, is going to be the time. It's going to be equal to the time where the cars cross, and therefore give you the time that the bicycle is ahead of the car. Now, this is going to end up, as you'll see, in a quadratic equation, okay? And there's the quadratic equation when the car catches up when it is still accelerating, and one where it doesn't. And I did this one and got negative numbers on this one, so it's going to be this scenario. So I'm going to get rid of this for now. And if you guys have questions later on that, we can go through this, but I don't want to make this video super long. Okay, so we have that situation. Now, the second question is going to be how far, what is the maximum distance ahead is the bike than the car at any one point. So when you go to velocity versus time, okay, you're going to have, when you have a constant acceleration, it's going to be a diagonal line like so. And then once it reaches its constant velocity, it's going to be straight like that. Now, as we've already pointed out over here, the car is going to be accelerating by the time it reaches the car. But in this case, where these two intersect, okay, is going to be the time, okay, it is going to be the time that the car is going the same speed. The car is going to go the same speed as the bicycle. So this time and this time are not the same. Okay, so we're going to go to part A, okay, and in part A, we want to know, okay, we're going to have this time right here, but we've got two different things. We've got the acceleration part, and then we have the constant velocity part. Okay, so we're going to figure out how much time it takes for the bicycle to reach its maximum velocity, okay? So we're going to have V final is equal to V initial plus AT. This is the kinematic equation number 2, what I call number 2. And we know that the initial velocity is going to be equal to 0. So we're going to have V final divided by A is equal to T. And our final velocity of the bicycle is 8.93 meters per second. And we know that the acceleration is going to equal to 5.8 meters per second. And that is going to give us a time of somewhere around a second and a half. So 8.93 divided by 5.8. And that gives us 1.539, so we'll call it 1.54. Okay, so the time is equal to 1.54. Now, that's just the time. That's just the time to this part right here. So now the time to this part, okay, is really going to be the trickier part. So what we know here is that the distances are going to be the same. Okay, so we're now going to use the kinematic equation number 3, which is going to be delta x is equal to VIT plus 1/2 AT squared. Okay, but on the bicycle side, okay, we're going to have two distances. We're going to have the initial velocity was 0, so we're going to have 1/2 AT squared, okay? And that's going to be the distance for this first part, okay? And which took 1.54 seconds. And then the second part is going to be plus, now in this case, it's going to be V final times the total time minus this initial time, okay, the time for section 1. This is 1.54, and that's going to be that section right there. So we'll put in numbers in here for a second. But that's the total time. Okay. Now on the other side, on the car side, we're also going to have an initial velocity of 0. So this is going to equal to 1/2 AT t squared. Now this is the total time. This t and that t are the same. Okay, now we can see that this is going to be a quadratic when we plug in the numbers, and we'll solve for that. Now, in the other case where we talked about the other one I did, if you were to add this final velocity of 22.3 times the time difference, that's where we got an answer that was not relevant. And so that's what we know here. So now if we plug in our numbers, we can kind of get this. So we're going to have 1/2 of 5.8. So 1/2 of 5.8 times 1.54 squared. Okay, so that was that first distance. That ended up being 6.88. Okay, and we're going to have 8.93 times this t minus 1.54. Okay, so remember, we have to take the bike is not going to be going at full speed for the entire time, so we have to subtract the amount of time it was accelerating. And then this is going to be 1/2 of 4, because our acceleration was 4 times our t squared. So we're going to end up here with plus 8.93 t, and that's going to be minus 8.93 times 1.54, which is going to be 13.75, 13.75. This is going to equal to 2t squared. We're going to take negative 13.75 and add 6.88 to it. And we're going to get 6.87. Okay, so now when we combine all these, we're going to end up with 2t squared minus 8.93t plus 6.87 is equal to 0. Okay, now when you solve for that and you put it in a quadratic equation solver or in your calculator, you're going to get a time that is equal to 3.45. I think when I did it, I got 3.47, which I think is just a result of the conversions. Okay, so this is that is our time, or part A. So that is the time that the bike is in front of the car. Okay, now we want to know for what is the maximum distance? What is the maximum distance? Okay, so as the bicycle accelerates, obviously it's going to be ahead. And as long as it keeps accelerating faster than the car is, it's going to get farther and farther ahead. But at a certain point, the bicycle is going to stop to accelerate and it can't go as fast. So therefore, the bicycle is going to be ahead until the car reaches the same speed as the bike, at which point the car will start to overtake it. So we're looking for this time. So the bike is accelerating faster, okay, a higher slope, and then it's going to level off here. So we want to know the time it takes for the car in purple to reach the same speed, and we know that speed. We know that speed is 8.93. 8.93. Okay. Now I am going to kind of shift this over so we can go the delta x. We're going to go the delta x for the bicycle is equal to 1/2 a times 1.54 squared. Okay, and that was that, and our acceleration was 5.8. Okay, we'll put that in there in a second. plus we have our maximum speed, which is 8.93, times the time that we're looking for minus 1.54, okay? Because at that time right there, that is also going to be the time where the bike was not going at its maximum velocity until it reached 1.54. So we don't have as much time right there. Okay, now that is going to equal to 1/2 the acceleration of the car times t squared. And this t is what we are looking for. So we are going to have let me see. So we're going to have 1/2 times 5.8 times 1.54 squared. That was 6.88. Okay. And that is going to be plus 8.93 times t minus 1.54. And actually what we can do is we can do the same thing for time as for the car. We want to know the time it takes for the car to get to 8.9 meters per second. So we're going to do the same. Time is equal to velocity divided by acceleration. Now remember, that only works if we have zero initial velocity. Okay, so now we're going to have 8.93 divided by 2, and our time is going to be about 2. This is 4, sorry. This is going to be about 2.23. Let's do the math. 8.93 divided by 4, 2.23. Okay, so we know that this time right here is 2.23. So now, how far has the car gone in 2.23 seconds? Now that's when we're going to do the 1/2 4 times 2.23 squared. And when we do that, 2 times 2.23 squared, that means the car would have gone 9.95 meters, whereas the bicycle would have gone 6.88 plus 8.93 times the difference of 2.23 minus 1.54. So 2.23 minus 1.54 is going to be 0.69 times 8.93. And that's going to be 6.16 plus 6.88. And that's going to be 13. And versus 9.95. So we're going to subtract this from this, 13 minus 9.95. And we're going to get 3.09 meters. Now, if we multiply that by 3.28, which is how many feet there are in 1 meter, times 3.28 gives us 10.14 feet. And we'll just call that 10 feet. So the maximum distance that the car is in front of the, or the bike is in front of the car, is going to be 10 feet. And that is the tricky one. That is the tricky one for problem set number 1. All right, so if you guys have further questions on problem set number 1, you guys can ask me in class or on Zoom, and I can go over those as well. All right, take care.